A very good afternoon to all, faculty members, colleagues, and dear students who are present here and also who are watching this event live over YouTube. It gives me immense pleasure to welcome you on behalf of the Department of Physics, Bangabasi College, Kolkata, to the first post-pandemic colloquium lecture. We are proud to have with us Professor Dr. Naba Kumar Mondal, or Naboda as he is well known to us in the Indian particle physics community. Though he needs no formal introduction, let me tell you something about him in short. Professor Naba Kumar Mondal earned his BSc Honours and MSc in Physics from Bardhaman University. He joined Tata Institute of Fundamental Research TIFR Mumbai in 1977 and worked with MGK Menon and VS Narasimhan on the Kolar Goldfields proton decay experiment, obtained his PhD degree from University of Bombay in 1983. He worked at Argonne National Laboratory, USA between 1985 and 86 for the development of the second generation proton decay experiment at Sudan Mines, Minnesota, and on the CDF experiment at the Fermi Lab, USA between 1986 and 87. In 1988, he returned to TIFR and continued his work on various accelerator and non-accelerator based particle physics experiments. He was involved in the CMS experiment at CERN, Geneva, and was the technical coordinator of the CMS Outer Hadron Calorimeter project. He was instrumental in the design of this subdetector and led the Indian team during its research and development phase. Professor Mondal was associated with the pioneering Kolar Goldfield proton decay experiment from its inception. He took a leading role in the design, construction, as well as in the analysis of the data. In 1991, his group joined the international collaboration experiment called T0 at Tevatron Collider at Fermi Lab. He was responsible for the design and fabrication of a large number of scintillate counters through wavelength shifting fibers to detect muons in the experiment. He played a leading role in the analysis of data collected by the D0 detector and was involved in the important discovery of top quark, which was the only missing quark of the standard model of particle physics. এই প্রসঙ্গে আমি একটা ছোট্ট এডিশন করে রাখি। আমি এমএসসি যখন পড়ি 1996 সালে, নবদা আমার যদি ভুল হয় একটু আমাকে কারেক্ট করে দেবেন, 1996 সালে আমি যখন এমএসসি পড়ি তখন টপ কোয়ার্ক ডিসকভার্ড হলো এবং আমি প্রথম নবদার নামটা আমি এমএসসি পড়াকালীনই শুনেছিলাম। He also used the D0 data to put strong constraints on the masses of the supersymmetric particles and extra dimension parameters. Professor Mondal also looked for subatomic structures inside quarks and leptons. He has published over 230 research papers and had edited several books. He has supervised 7 students for their PhD degrees. Professor Dr. Naba Kumar Mondal has served in various capacities in the D0 and CMS international collaboration experiments. He is a member of the D0 Institutional Board and CMS Collaboration Board. He is also a member of the International Neutrino Factory Steering Committee, OECD Astroparticle Physics International Forum, and spokesperson of the India-based Neutrino Observatory, INO. He has also led a team of physicists and engineers from several research institutes of India with a motivation to set up a full-fledged underground laboratory in India for carrying out front-ranking experiment in the field of neutrino physics. Naboda is now INSA, means Indian National Science Academy senior scientist at Shah Institute of Nuclear Physics, Kolkata. In the recognition of his contribution towards the D0 experiment, American Physical Society had invited him to present the Esther Hoffman Beller Endowment Lecture in 2001. Professor Mondal is a fellow of the National Academy of Sciences, Allahabad, Indian Academy of Sciences, Bangalore, and Academy of Sciences of the Developing World, Trieste, Italy. He has been awarded J.C. Bose Fellowship by DST Government of India. So, without much delay, let me invite Naboda on stage and ask the students to do the favor. Amrita and Sanjay. Uthe aay.
Thank you for such a warm reception, and Do I need this? Huh? Oh, that will make me handicapped. Okay. Oh, more things. Huh. Thank you. Thank you. Thank you. Thank you, Pastor. Thank you, all the faculties of Bangabasi College and the students. It's on. Yeah. So, so story of my talk today is neutrinos. So I'm going to tell you a story of neutrinos for the next 45 minutes or so. And do you have a one or something? Quantum name. Oh, okay. Okay. So let me start my talk with with this quiz. So here are the pictures of 8 people, and there is something common about these people. And can you identify them and tell me what are these pictures are there? They're all famous people. Well, they're all Nobel laureates. So that is the one common thread. They're all Nobel laureates. And but then there is something more common, actually. Okay, so there are Nobel laureates. So let me just go to that. There. What is this? Okay. So they're all Nobel laureates, but there is something more common among them. They got Nobel Prize for their research on one particle, and that particle is neutrino. So this one particle, which is known as ghost particle or Bhuture Kona and so on, has already earned 8 Nobel Prizes and more are on the queue. And definitely we know there are important discoveries to be made in the neutrino physics which will fetch Nobel Prize in the past. So here are the people on the top. You can see the name of them, Leon Lederman, and then Mel Swartz, and Jack Steinberger. They got their Nobel Prize in 1988 for the discovery of the muon neutrino. I'll come to that later. The next, the single man, is Fred Reines. Fred Reines who is the discoverer of the neutrino. Actually, he discovered the electron neutrino in 1956, but he has to wait a long time. He got his Nobel Prize only in 1995. Next two are Ray Davis and Koshiba-san. Ray Davis got his Nobel Prize for detecting neutrinos from the sun. Koshiba-san got his Nobel Prize for discovering the neutrinos coming from the supernova explosion. And last in this one is Kajita-san and Art McDonald. They got their Nobel Prize for discovering what you call neutrino oscillation. And there are more things to come. So this is the story of neutrinos. So it's so exciting, but actually when the particle was first introduced, people didn't know what to do with that particle even. Okay? So let's look into our elementary particles. This is the periodic table of the particle physicist, equivalent to your chemistry periodic table. This is all the building blocks that we have, of course, in nature, and that's are all the particles. So in this, actually, there are some particle which is very important. So for example, this is the up and down quark, and this is the electron. And you know they are very important because all the matter that we see, everything we are made out of, you, me, all the chairs, the whole universe, as we know of, is made out of this. Because 2 up quark and 1 down quark made a proton, and 2 down quark and 1 up quark made a neutron. And those protons and neutrons are in the nucleus of every element. And then the electron goes around it and make the atoms of all these elements, and they will combine for molecules, make structure, and so on. So this is all the particles that we know of. Of course, this electron, this up and down quark has their heavier cousin called charm and strain, top and bottom, but I'm not telling you the story today about them. And also, the electron has its cousin also there, heavier cousin called muon and tau meson. So these are the called leptons, and those are called the quarks. They make. But my story is none of these particles. So actually, the whole universe is made out of these particles, but I'm not talking about those particles. My story is actually is about these three particles. These are the particles, they are associated with those leptons. The electron has a partner called electron neutrino. A mu meson has a partner called muon neutrino, and tau meson has a partner called tau neutrino. And these are the particles that I am going to talk about their stories and so on. Now, as I told you, the electron, okay, there is a little more about that. Why we want to learn about these actually? Those particles actually, why do we need them? I mean, just for studying, what is happening inside the matter, what everything is made out of? No. Actually, at some early stage, very, very early stage, the whole universe was made out of only a soup of those elementary particles. There is no such thing like a chair, table, and a star and galaxy in those days. It was a hot soup of elementary particles. So by studying those elementary particles, now, because we can't get any information from those times, from our normal looking at the sky. Looking at the sky, the earliest information we get is after the creation of the Big Bang, 3,000 years after the creation of the universe. Before that, all the information is blocked to us because the only information that comes from this universe is through looking by the telescope. That means from the light that comes out of those objects. And light was not coming out till 3,000 years after the creation of the universe. So if you want to get any information earlier than 3,000 years of the age of the universe, you have to depend on the research on the elementary particles. In particular, the neutrinos. See about 3-degree blackbody radiation, microwave blackbody radiation. Have you heard about that? This is actually coming from all directions, a radio wave which was created just after the 3,000 years after the creation of the universe. So by studying photon, we can study up to, as I told you, 3,000 years back, after the creation of the universe. However, if we study neutrinos, there are some neutrinos which has come out after just 1 minute after the creation of the universe. So earliest picture of the universe will be through those neutrinos. But those neutrinos are so low energy today, we don't know how to detect them. But probably in one day, we'll detect them. That I'll come later. Anyway. What is this? No? Why is it not going? Okay. So again, it has come. Fine. Okay. So now, why neutrinos are there? See, it was actually, you have heard about beta decay. You might have not studied about beta decay. There are some radioactive elements, okay? And they emit what you call alpha ray, beta ray, gamma ray. And we know from there that these alpha ray, beta ray, gamma ray, they has to have a fixed energy because alpha rays emit between when a nucleus gets converted to another nucleus. So difference between them should come out at the energy of the alpha ray. Same thing happened to the beta ray. Same thing happened to the gamma ray. So that means when a nucleus gets converted to another nucleus and we get a particle out of that, then to conserve the energy, you have to have energy difference between these two nucleus comes out at the energy of the particle, that is alpha, beta, or gamma. That's true for alpha and beta. They are of fixed energy. But when they started looking at the energy of the beta rays, that is the electron or positron that comes out of the radioactive decay, then they found that they are spread out with energy. Some will come with very low energy, some will come with high energy. And if you collect enough of them, you can plot them like this. This is their energy and how they are distributed. Okay, this is not, if it is a really true, then they should have a fixed energy like this, one line at a fixed point. So that was a puzzling to the scientists in the early part of last century, around 1920 or so, and people are wondering what is happening. So they are even thinking that in beta decay energy is not conserved. So if energy is not conserved, then you don't have to worry, right? Because there is no problem. But that's too much, because energy conservation law is one of the pillars of modern science, modern physics. So you cannot just give up energy conservation law. So then, at that desperate situation, Wolfgang Pauli in 1930 is a very famous theoretical physicist who has given us Pauli exclusion principle. He came up with the idea in a desperate situation. He said, and he sent a postcard. He was to go to a conference and talk about this result, but he didn't go there. He just sent a postcard to that conference saying that to save this one, I am, he apologized that he is introducing a new particle. So what he says, that when a beta decay happening, then not only beta decay, another particle is coming out of that process. So this is something like here. So for example, when a carbon-14 emits an electron, it gets converted to nitrogen-14, okay? And one electron comes out. So that's the process we saw. But if this happens, then the energy difference between carbon-14 and nitrogen-14, that energy has to be taken away by this electron. And this energy is fixed. So this electron should have a fixed energy. However, since this is not happening, then he said, okay, I am actually proposing that in this process, another particle is emitted. Not only electron, but another particle. It is a neutral particle, and that is taking away that remaining energy. Okay? So in the language of kinematics, you will learn later that it is called a three-body decay. 1, 2, 3. Three-body decay. It was earlier two-body decay. So in three-body decay, this guy, because it is heavy mass, it will conserve the momentum, but it doesn't take any energy because of the mass. All the energy will be taken by these two. And they will share the energy. Now, because they are sharing, it is possible. So that is how he introduced the neutrino. But then, so then after that, the 1936 around, Enrico Fermi came and he gave us the theory of beta decay, beautiful theory of beta decay, which is we know, even learned today in the textbook about the weak interaction, starting of weak interaction. And then, but this particle was not discovered. Years after that, proposed in 1930, it never discovered. So now ultimately, because Fermi's theory, Fermi actually did his calculation, he showed that the interaction probability of neutrinos is extremely small. It will be almost difficult to detect. He said almost not possible to detect. But almost not possible is not impossible. Almost not possible means you can try. And then this guy, those Fred Reines, I have introduced Fred Reines to you in my first slide. He and his colleague, Cohen, Fred Reines was involved in the Manhattan Project, as you know, making the atomic bomb during the Second World War. And just after the war, he knew everything about nuclear, reactors and so on. Reactors are coming up. Nuclear reactors are very intense source of neutrinos because inside the nuclear reactor, the fission happens. And when the fission happens, they create lots of neutrons and other radioactive elements which will be continuously radioactive, and that's why you cannot go close to a nuclear reactor. You know that? So it is emitting lots of neutrinos. He said, okay, now I have this heavy, strong source of neutrinos. So I will do my experiment. Because it is highly improbable, but maybe I'll be able to detect neutrinos here. So that's what the experiment. The project was called Project Poltergeist, Poltergeist means ghost particles, actually ghost, actually. So this project was actually detecting ghosts, and that's what, from that time, the neutrinos are infamous with the name as ghost particle because it is so difficult to detect them. So what it did, okay, the reactor will produce anti-neutrinos. Actually, if you see that, the reactor will produce anti-neutrinos, not neutrinos. But these anti-neutrinos will come and they'll interact with a proton here, okay, inside this one. So antineutrinos will come hit with the proton, and then process, it will produce a positron and a neutron. Okay? And positron will immediately combine with a new electron, and they will, convert into energy. So electron will annihilate by a positron will be annihilated by electron and produce two gamma rays immediately. However, so you'll get a pulse. Okay, gamma rays will be detected if you have detector here. But then the neutron will travel some distance and it will be absorbed by the cadmium. Okay, and then it will convert cadmium 113 to cadmium 114. This is an isotope of cadmium, and this isotope of cadmium will go to excited state and it will come back to the ground state with the emission of gamma ray. So what is the signature? The signature will be first a positron and electron annihilation with gamma rays. Then after a few microseconds, the neutron will wander in the liquid and will produce further gamma rays. So this delayed coincidence, what they call, first gamma rays and second another one, will be an unique signature of a neutrino. And that's what Reines did the experiment in 1956, and he immediately sent the telegram to Wolfgang Pauli saying that I have discovered your particle. And that's how the particle came into picture. Okay, so now about a little bit, so let me go. Neutrinos were, 1956, within a short time, in 1965, in India, in Kolar Goldfield underground, the scientists were doing an experiment to detect another piece of neutrinos called atmospheric neutrinos. I'll talk about that neutrinos, and they had also a competitor. He was doing an experiment in South Africa, mind. That competitor is no less than Fred Reines, who was the discoverer of the neutrino. But the Indian team beat the Reines team by 2 weeks by publishing first their result, which is came in this physics letters on 15th of August 1965, and this paper came on the end of August 1965, actually published. Okay, this is 30th of August 1965, so 2 weeks different they were published. And later on, we also have in Kolar Goldfield, when Parth was talking about, by this time I was doing proton decay experiment, and we saw many, many such neutrinos. And this is a beautiful event of neutrinos. It is upward going. It is coming from the bottom of the Earth. And then inside our detector, and the neutrinos are coming here, and then interacting and producing a muon and a pi mesons. And neutrinos cannot be detected by itself because neutrinos are neutral particles. Only charged particle can be detected inside your detector. Okay, so that is why you see nothing, and then suddenly inside the detector you will see neutrinos, and then you can see those. There is a different picture I don't want to discuss here. So now let's talk about all the neutrinos. Why so exciting? Where do they come from? They come from every source, everything you can imagine. Let's talk about. I have talked about neutrinos are created during the Big Bang. All particles that we have in the universe are created during the Big Bang. Okay, quarks, leptons, everything. So all the neutrinos. And those neutrinos are now has decoupled from the Big Bang, and just about 1 minute after the Big Bang. That's why I told you that they can give you information. If you can detect those neutrinos, we can get information how the universe was look like just 1 minute after the creation. Okay, but very difficult because their energy is extremely small today. Because with the expansion of the universe, the neutrinos are also slowed down. Okay, their energies are decreasing. Their wavelength is increasing. Their energy today is something like 10 to the power minus 4 electron volts. So very, very tiny energy. But they are very, very abundant particles. Every cubic centimeter of the space of the universe, we just told you, inside there are 330 neutrinos per cubic centimeter. So imagine how many neutrinos created during the Big Bang is filling this room itself. So this is the second most abundant particle in the universe. The most abundant particle of the universe is photon, the light. That is whatever created during the microwave, at 3 Kelvin temperature. So that number is around 410 per centimeter cube. And this is the second largest number, not quarks, not electrons, not this thing, it is the neutrinos. Quarks and electrons are tiny number compared to the number of neutrinos we have in the universe. Then these are Big Bang. Then neutrinos from the sun. What is happening in the sun? Why do we get the energy? Our source of energy is sun. Our future energy is sun. Everybody says. What's happening in the sun? Who is giving that energy? It's simple. Inside the core of the sun, 4 proton is converted into helium. If you take the difference between them, that is around, you get energy around 26 MeV of energy, and in the process, 4 proton is getting converted into one helium. One helium inside, what is there? Inside helium, there are 2 proton and 2 neutron. That means 2 of the proton is getting converted into neutron. When proton is getting converted into neutron, it is producing this electron, and it is also, positron, and also producing this neutrino. Okay? So then it is neutrino source. This neutrino has been detected by Ray Davis. For that he got the Nobel Prize. Then this is during the sun, a mainstream star. But when this, at the end of their life cycle, a star may explode. If their mass is more than Chandrasekhar mass limit, then it will explode into a supernova. And during that time, all the binding energy, 90% of the binding energy of the exploding star, get converted into neutrino. So during that time, at that moment, when the star blasts and supernova explosion happens, for some 10 seconds or so, there will be intense burst of neutrons will come out of all directions of that star, in all directions. So if you have a detector, you will suddenly say a just bunch of neutrinos will be detected in your detector, and then again it will be quiet. Such an event was observed by the Kamiokande experiment, for which this, as I told you, that Koshiba-san got his Nobel Prize. Okay, now atmospheric neutrino. The cosmic rays come and hit our atmosphere. Cosmic rays come and hit our atmosphere. Atmosphere, when it hit, it produces many particles, mostly pi meson. Those pi meson are unstable particles. They will decay and they will produce muon. Here you can see those pi meson decay producing muon. But along with muon, they will produce muon neutrinos. And these muons will further decay and produce electron neutrinos. So in the process, when this cosmic ray comes and hits our atmosphere, a shower of particles, muons, neutrinos, electron neutrinos will be produced. They're quite high energies. These can be detected underground. In fact, the INO experiment, India-based neutrino observatory experiment that we are thinking of in India, is to detect those neutrinos and to study further. Then we have ultra-high energy neutrinos. There are some neutrino sources in the sky. They produce very, very high energy neutrinos, maybe something of the order of 10 to the power 12 electron volt, or even 10 to the power 14, 10 to the power 16. And those neutrinos are so high energetic, and they will be coming neutrino cosmic ray sources and so on. Then there are radioactivity at the core of the Earth, because the heavy element of our Earth is basically sitting in the core. The core has lots of uranium, thorium, and so on. Those uranium and thorium is continuously decaying and keeping this core as molten state. But in the process, they are producing neutrinos. That neutrinos are coming out, and you can detect them. So this is the core of the Earth. Then there are neutrinos you can create. So far I have talked about natural process of creating neutrinos. But you can process neutrinos, man-made accelerator. You can produce them in particle accelerator. In the particle accelerator, you energize the proton and hit another particle. In the process of the collision, they'll produce new particles, and like pi meson. That's like what happening there. That can happen in the accelerator. And those pi meson will decay and produce neutrinos. Okay? So that is how you can produce neutrinos. And last but not the least, I have told you reactor neutrinos, right? That's how the Fred Rines used to discover the neutrinos. So reactors, all reactors are very intense source of neutrinos. If you close a typical nuclear reactor, like you go to Kudankulam, we have this giga electron volt power generation by the nuclear reactors. Two of them are working. Each of them, if you go close to them, will produce something like 5 into 10 to the power 20 neutrinos per second coming out from those reactors. Okay? So imagine the number. So they can be produced there, and you can study them. Well, so now with all these things, now let's see what is happening to you. So every second your body receives about 1 trillion neutrinos from the sun, each of you. 50 billion neutrinos from natural radioactivity to the Earth. From the Earth, it is going 50 billion neutrinos going through your body all the time, produced at the core of the Earth. 10 to 100 billion neutrinos from nuclear plants all about the world. Doesn't matter whether it is in America or whether it is in Russia or China or India. The neutrinos can travel and come to you. How many reactor-produced neutrinos are going through your body every second? Is something like 10 to 100 billion neutrinos are going through that body. So imagine how many neutrinos are going through your body every second. That is not all. That is not all. You should also remember, you all are source of neutrinos. You are producing neutrinos. Your body, on an average, has 20 milligram of potassium 40. Everybody, it may be take, give and take, depending upon body composition and so. And this potassium 40 is radioactive. Your body has radioactive element. That means we emit about 340 million neutrinos per day. Each of us is producing 340 million neutrinos per day. And they are just, we run from our body at the speed of light and they run up to the end of the universe. So your body is becoming, or body parts becoming the part of the universe from the time you are born till you die. So now, in India that has that when some great man dies, they will take their ashes and spread all around the country because they want to. But I tell them that don't do that because your body parts is getting part of the universe all the time anyway. You don't have to do that. So now with all these things, you must be scared, right? So many neutrinos are going through your body, and that's what the politician created the fear monger in Tamil Nadu, told them the neutrinos are dangerous for us. So now what these neutrinos will do to you? Let's see. How dangerous are they? Typically, a neutrino has to zip through, I don't want to count the number of zeros. There are something 18 or 19 zeros are there. If I put so many human beings in a line one after another and shoot one neutrino through them, then there is a chance of this neutrino will get stopped at one of the person's body. So that means it is actually no problem for you. Neutrinos are going through your body doing nothing. So it is a good news for you, but bad news for a neutrino hunter like me. Because if it is not getting stopped, how I am going to detect them? That's the problem. So that is why all neutrino detectors that you will see has to be very big, very small. It has to be some 5-story building size or even a kilometer cube ice at South Pole and so on. So now, how do we detect neutrinos? So let's go through that. So we have seen that in the sun, 4 proton is getting converted into a helium, and in the process 25 MeV energy and 2 electron neutrinos. Remember this is electron neutrinos. The sun core produces electron neutrinos. So I told you there are 3 kinds of neutrinos: electron neutrino, muon neutrino, tau neutrino. But sun is producing electron neutrinos only. So now, these neutrinos will come and hit some matter, and sometimes, so many people, but if you have, instead of that 10 to the power 20 neutrinos, so one neutrino going through 10 to the power 20 people will stop. But if 10 to the power 20 neutrinos will come, one of them will stop inside you. So because of the neutrinos are high, and if you can a large number, then you can detect them. So how to detect them? So this ideas came by Bruno Pontecarvo, who plays a very important role in the neutrino physics. He said that if you have a source of chlorine-37, that these neutrinos will come with energy, and if this neutrino energy is more than 800 keV or 0.8 MeV, then this will convert by this chlorine-37 to argon-37, and is this the energy, threshold energy. So and then this argon-37 is radioactive, and it has a lifetime of 35 days. So if you can collect them and count this number of argon-37, and then you know how many neutrinos have come and interacted. So then from there you can calculate the flux of neutrinos. Very easy to say, but difficult experiment. So who will take the challenge? So there was a guy from Brookhaven National Lab, and he was not a physicist. He was a chemist, so he didn't know what trouble he is going through. So he said, I'll take the challenge. So Ray Davis is a chemist, and he actually built, ultimately, 100,000 gallon of chlorine experiment in Homestake mine in South Dakota in United States, under mine. Why underground? Because in the surface, these experiments get disturbed by cosmic rays. So all neutrino experiment has to be underground. Okay? And they don't go underground to hide some radioactive elements or some of the politicians of Tamil Nadu are saying they want to go underground to hide themselves from the radiation that is there in the Earth's surface, that is cosmic rays. So you have to go underground. So 100,000 gallons. And when he was doing that experiment, a very difficult experiment, I will just skip this one. This is the different process of how neutrinos are and how basically there are three chains. This is actually the main called PP neutrinos, where you will see that hydrogen is converted to helium, and these are also hydrogen is converted to helium, but different process. So these are the three processes, and their energy spectrum is given there, and ultimately the Ray Davis experiment was mostly sensitive to these neutrinos. This is called boron neutrino. Basically, chain how hydrogen convert into helium. There are different pathways by which the hydrogen gets converted into helium. Okay, so three different pathways. This is called boron neutrino. This is called beryllium neutrino. This is called main PP chain. Anyway, here the flux of the neutrinos are quite low, but one advantage was their energy was higher. I told you that chlorine experiment is sensitive to 0.8 MeV neutrinos or higher. So that is where is somewhere here, and then this will be detected by this Davis experiment. He did the experiment, okay? So this is the experiment he did. He put a big container of C2Cl4, and then that is the chlorine. The neutrinos sometimes come and convert this chlorine 37 into argon 37, and he will every month he will collect those argon 37 atoms from this huge container. Don't ask me how they will do that, because that is actually a talk by itself, but it is a beautiful experiment. And he will collect them, he will put it into a proportional counter, and then let them decay in the 35 days lifetime and count their number. He did count the number, and this is what he found. He did found neutrinos. Actually, these are not zero. So he did found neutrinos. There is no problem. So congratulate to him. But he has a problem. He was expecting the number of neutrinos as shown by this dotted line. And he was getting these numbers. Okay, and this experiment he ran for almost 20-25 years. And then he continued that run, and all the time he was getting less. 1/3 of the neutrinos he was expecting. This is if you take the average of this will be the number, and this will be the error bar. So he did see neutrinos, but he saw 1/3. So that is a problem. So pardon? Yeah. So statistics. If you combine this all, number of events. So this is all. Of course, these are all few number of events. So you have to combine the whole run, and then this is what you will get, statistics. Okay. So now, so Ray Davis was doing, and everybody was actually telling him, he's a chemist, he doesn't know how to do a physics experiment, so it must be all wrong. His result is wrong, he doesn't know how to do an experiment. And he was not perturbed. He was carrying out his experiment, he was calibrating his experiment, he's improving his method, and he was proving to them that he's doing everything right. Around that time, in mid-80s, the Kamiokande experiment was designed for a different purpose, to detect the decay of proton. That was my thesis experiment, something like 5-6 years before this experiment. But this experiment is basically underground water reservoir. So it is a clean water of this one is up to 5 kiloton, and then they converted it to a 50 kiloton super Kamiokande, where all this surrounding walls of that water reservoir is full with photomolecular tube. They are like a photographic eye, watching the water. And whenever something happens, they detect. What can happen? A neutrino can come from the sun, and it will hit an electron, and this electron will start in the forward direction with some energy of the neutrino. So neutrino energy will get converted to the electron energy, and electron will start moving inside the water. And if its electron's energy is such that the velocity of that electron will be more than the velocity of light in that medium because of the refractive index. And then it will produce a light called Cherenkov light. And this light will go in a cone, okay, around the particle. The particle is going like this, and a cone of light will go like that. And then you have the photomultiplier tube on the wall, and they will detect those lights in the ring, okay, only in those places because it is going in a cone. Only in the periphery of the cone, the light will be detected. And then, not only that, then they found that yes, those electrons are coming, and they are coming from the direction of the sun. Because other direction they didn't find neutrinos, but then suddenly they saw, when they're looking inside the sun, they saw that neutrinos are coming from there. So they also saw neutrinos from the sun, okay? But the problem was that they confirmed the result of Ray Davies. This is Ray Davies' result, chlorine experiment. This is what you expect, and this is what they observed. This is the Super Kamiokande experiment. Again, this is what they observed, this is what they expect, 1/3 or half maximum. And then continued with another experiment. This is also saw less. Now all three experiments seeing less neutrinos you have to take very seriously. So what can be wrong? There can be two hypotheses. One is really sun is not that hot. If it is not that hot, it will produce less neutrinos. Then okay, then less neutrinos means fine, it will explain. So then something wrong with our understanding of the sun. But the astrophysicists told them, no, nothing. We know the sun very well, and you have no problem with the sun, so your particle physics will not apply here. You go and find your solution in your experiment. So then the theorist has to work very hard, and then maybe neutrinos behave differently compared to other particles. They say it behaves differently. What is that different? So that is come neutrino oscillation. So that is actually, I will tell you, first proposed by Bruno Pontecarvo, the guy who just told about the chlorine experiment. He is a fascinating character. His story is also to be told to you. You should read actually. He was a fantastic character. He is one person when many scientists after the war is defecting from Soviet Union to Western world. He is one scientist who defected from Western world to the Soviet Union. And he stayed there till he died actually. He's an Italian, but that is how he is. So for Newton, so what is his theory? He actually proposed first, and then it was revised by these three Japanese, Maki, Nakagawa, and Sakata in 1962, and finally, again it was revised by Pontecarvo in 1967. He says the neutrino weak eigenstate may be different from mass eigenstate. What does it mean? I don't know how much quantum mechanics you have studied. So that means, there's a superposition of states. So this nu1 and nu2, these are neutrino mass eigenstate. I mean, those states have fixed mass. And now, nu e and nu mu, these are flavor eigenstate. So nu e, as I told you, is associated with electron. Nu mu is associated with muon. They are partner of those. So electron neutrino is, let us say, is a superposition of those two mass eigenstates. And the muon neutrinos are to the orthogonal superposition of the same mass eigenstate. Okay? And if that happens, but then in the process, you will only create electron, as I told you at the beginning, remember, in the sun you are creating electron neutrinos, not muon neutrinos. So at neutrino, when it is produced inside the core of the sun, it is electron neutrino, no question. Now the electron neutrino, you write it in the mass eigenstate form. So nu e will be nu1 cos theta plus nu2 sin theta. Now you have studied stationary states. Stationary states over time, the nu1 and nu2 are stationary states, right? So over time, they will evolve. They will pick up a phase factor. And those phase factor is that e to the power minus IE1t and e to the power minus IE2t. They have different masses. And ultimately, if you carry out your mathematics little bit, then you will see that though I have started at time t equal to 0, a pure nu e, that is nu1 cos theta and nu2 cos theta, after some time, that may be a different composition. That means there is a probability, even though on the original neutrino source, there was only electron neutrino, after some time, some of those electrons will get converted into a muon neutrino or a tau neutrino. And what is that probability? That probability is given by this formula here. There is a mixing angle. This mixing angle, theta, is here. And then delta m square term. This delta m square is the mass square difference between those two neutrinos. Okay? So if delta m square non-zero, remember, if delta m square non-zero, then this probability will be non-zero. Okay, this is number one. So what does it tell you? Simply, that's one thing actually it is giving me two. It is giving me a solution of the solar neutrino problem because electron neutrino I am checking, but it got converted into something else, muon neutrino. Not only that, it is also telling us that neutrinos have mass. So far, standard model of particle physics, neutrinos are massless. So, and the solution of that one immediately give you mass of the neutrino. Tiny mass, but a mass. And if that is true, that means it is the first indication of beyond standard model physics. Okay, neutrino mass is not there in standard model. Anyway, so this is the formula. So that means it is telling you that if that is true, that explains. So Ray Davis was doing experiment and he was looking for what? He was looking for electron neutrino. But if by the time the sun started by electron neutrino, some of them got converted into muon neutrino, tau neutrino, he was not looking for those. So he was seeing less. So if you are an experimentalist, what will be the solution? I should look for. I should design an experiment to detect all three of them, not just electron neutrino. And that's what the next phase of experiment was done. So this one I actually avoid. Okay, this experiment. So this is the experiment was done in Canada, okay, Sudbury Neutrino Observatory, SNO, where instead of water that Kamiokande they use heavy water. Heavy water is D2O. D2O instead of H, you have in the nucleus a proton and a neutron. Okay, a proton and a neutron when it comes. So if you like to say additional what is happening, if the electron neutrino comes, of course it will produce two processes. How the electron neutrinos will be detected? Electron neutrinos will come, it will knock out the electron like water itself, and that electron will produce a Cherenkov light, like in the Kamiokande experiment. Good. Or the electron neutrino will knock this, neutron and convert into a proton and electron, and the electron will produce Cherenkov light. So this is okay. This is both this process is detecting like old experiment electron neutrino. However, there is another process that experiment can do, that is here. So this is, you see, the neutrino of any kind. Doesn't matter whether it is electron neutrino or a muon neutrino or a tau neutrino. That can produce a neutral current interaction. So it will hit a neutron just like that, but not convert itself. The neutrino will go as it is. A muon neutrino will go away a muon neutrino. A tau neutrino will go away a tau neutrino. So neutron will come out, okay, from the deuteron. And the neutron, in that deuteron, heavy water, if you also mix salt, okay, sodium chloride, and in that sodium chloride there will be chlorine. The neutron will be absorbed by the chlorine 35 and get converted into chlorine 36. And just like the Ray Davis experiment, this will be in excited state and will come back to the ground state by producing gamma rays. And those gamma rays will have a total energy fixed around 8 MeV or so. So by detecting that, you will be able to detect all three neutrinos. Okay? Now you have a process of detecting electron neutrino. You have a process of detecting all three neutrinos in the same experiment. So what is the result? Beautiful. Here is the result. So here was expected and here was observed. Problem solved. And we got neutrino oscillation and we got mass of neutrino. So this is the story of neutrinos so far. So you have so far seen this experiment. So now same thing happened for the atmospheric neutrinos in the Kamiokande experiment. They are detecting muon neutrino. And muon neutrinos also, they found less muon neutrinos when the neutrinos are going in the upward direction. Okay, that means they have enough time to oscillate, but the downward going neutrinos here, cos theta less than greater than 0, they are not seeing that oscillation. They are matching with the older. That means they are only coming through some 10-20 kilometers, so there is not enough time for them to oscillate. The wavelength was not good enough, big enough, but upward going neutrinos were giving oscillation. So this experiment gave Nobel Prize to Koshiba, and this earlier Snow experiment gave Nobel Prize to Art McDonald. So they too solved and put neutrino oscillation on the firm footing through their experimental data. So you see, neutrino physics is always experiment driven. And then finally, of course, I have only talked about two neutrino oscillation, right? Nu1 and nu2, nu e and nu mu, but in reality, there are three neutrinos. So that one actually I have given you as an example. The real theory is this one. You have three flavor eigenstate, so you have a mixing matrix and you have the mass eigenstate. So you can convert nu e in terms of this, mixing matrix and the nu1, nu2, nu3. You can write it down, and then correspondingly there will be three mixing angles. So it's like a rotation of your 3D coordinate system from one frame to other, Euler angles, if you remember, your classical physics. Okay, so then it will be this, what is C12 and 13, these are the cos theta and sin theta. C for cos theta and S for sin theta. So there will be three angles, C theta 12, theta 13, and theta 23. You will see that these three angles will be combinations of those. That is actually connected to the Euler angle. So I am not going to detail. But this is not classical things. So this will be a complex matrix. This matrix will be a complex, so there will be a phase also will be there. Just like we have seen in the quark sector, there is a phase. Here also there is a phase, and the phase is may give us, if we can detect that, may give us CP violation in the neutrino sector. And this is the important part. So now the next experiment, already we know about the values of these angles reasonably well, but the next set of experiment has to detect these angles very, very accurately. Number two, we have to measure if this delta is non-zero. If this delta is non-zero, there is a scope of a CP violation in the neutrino sector. That's why it is exciting. So for now, I'm just to give you an example. The neutrinos experiment can have different kind of source, different kind of detector. Here you can, for example, a probability of a muon neutrino. If you just study muon neutrinos, like atmospheric neutrinos, then you will be measuring theta 23, okay? That theta 23, and you will be measuring delta m square 31. If you measure the electron neutrino, just like from the sun or from reactor, then you will be measuring theta 13 and theta 23. Here will be somewhere theta 23. Here will be theta 13, and this is theta 12. Okay. Oh, sorry. Here theta 23. This will be coming here, and this will be measuring theta 13 and theta 12. Theta 12 we have measured already in the solar neutrino. That is theta 12, and theta 13 we have measured in the reactor experiment. And theta 23 we have measured in that in the atmospheric neutrino experiment. So we have measured those. We have measured also all these masses, but we can measure it much more accurately. So, what is the most important questions in neutrino physics today? So what we have to understand. We have already understand so much. So we know the neutrinos have mass, but still we do not know that nu1, nu2, nu3, those are the mass eigenstate. We don't know yet whether nu3 is the heaviest or nu3 is the lightest. So then that means we can have a scenario where nu3 is heavier than nu1, nu2, or we can also have a scenario like nu3 is lighter than nu1, nu2. Why this problem is coming? Because in that, if you see, in that one is delta m square is m1 square minus m2 square. It is measuring the delta m square. Okay? We need to know the sign of the delta m square. Okay, basically. So then you will know whether it is up or down. This is still unknown, and this is where the India-based Neutrino Observatory was trying to detect these particular properties of neutrinos, whether it is, so it solved the problem of mass hierarchy, what you call, which is heaviest, which is lightest. But then there are other problems. Why the neutrino is so light? Because we know the neutrino have mass, but their masses is even much less than electron volt, maybe milli-electron volt or even lower. Whereas all the other particle masses are million electron volt or higher. So why there is a big gap? So what is the reason for this low mass of the neutrinos? whether they can be Majorana particle and so on, and that helps you to understand. Or neutrino is its own antiparticle, or a neutrino and antineutrinos are different particles. That also you have to understand. So these are the different physics topics that we have till today to be remaining. And then there are, in around 2016, there was a paper, there was actually an article in Nature magazine. They talked about 4 future famous or important experiments that is coming up in the world which will solve the neutrino problem. And those 4 experiments are Zuno in China, they are coming up. This is INO in India, that is supposed to have started already, but we couldn't. Then Dune in the Fermi lab, this is they are making ready preparation, and this is Hyper Kamiokande in Japan. This is coming up. And these 4 experiments together will solve the neutrino problem mostly. I mean, there is some, it will not solve, for example, whether neutrino is its own antiparticle and so on, but major oscillation-related problem will be solved by these experiments, and they are very important. So, for example, Fermilab experiment, what they are doing, it is a very interesting experiment. They have an accelerator in Fermilab. They are producing neutrinos and directing the beam at an angle so that it reaches the surface after traveling 1200 kilometers. This is Chicago, and this is South Dakota, in the west of, 1200 kilometer west of this one. And so this is actually why, because they want to give enough path for the neutrinos to oscillate. Because oscillation is the main thing. If you do not have enough path length to travel, then they will not oscillate. So to give that oscillation path length, and then from there, they will study both muon neutrino and muon antineutrino. And from there, they will study whether the neutrino and antineutrino behave differently. If so, that means they will be looking at CP violation. Sorry. So they will be looking for CP violation. This experiment is for CP violation. And their detector is fantastic. They will have, there are, again underground, at South Dakota, there will be liquid argon. And in that liquid argon, the muon neutrino will come and produce a muon, and they will produce a track inside the liquid argon very accurately. They will be able to measure their number and energy. And they, from there, I'm not going to details here, how they will study the CP violation. Hyperkamiokande, they will have beams from the KK accelerator in Japan. Also, they will be studying atmospheric neutrinos. And they will also have a detector at where the Kamioka experiment is located, and a second detector may be in even South Korea after traveling a large distance under the sea, and they will put a detector there and to solve the problem. Of course, this South Korean part is not yet approved. They are only talking about that. Then the Juno experiment. This experiment will be located 50 kilometers away from a very strong source of reactor neutrinos, and they will be like us. They will be sensitive to the mass hierarchy. So they will study, this is liquid scintillator 20 kiloton, huge liquid scintillator. They will put underground and then watched by photomultiplier tubes and so on. Okay, and then this is INO. If we have want to build, and it is supposed to go under a mountain, and then will be located, and it will be a 50 kiloton magnetized calorimeter. So this detector will be detecting atmospheric neutrinos. We don't have accelerator. We will be using only God-given neutrinos by cosmic rays, and using both muon neutrino and muon antineutrino, we will have a magnetic field. Whole detector will be magnetized, and then we'll be able to identify each event, whether it is a neutrino event or an antineutrino event, because a muon neutrino will produce a mu minus, and a muon antineutrino will produce a mu plus, and in a magnetic field, the mu plus and mu minus will bend in the opposite direction. In the magnetic field, a charged particle will bend, but they will bend in opposite direction. From their curvature, we will be able to know whether it is a neutrino or antineutrino, and we will be detecting that. Okay, so actually now a little bit about the INO experiment. We have started this, and this is a big project, science project in the country. So we also started to develop everything from scratch in the country. And the first part of that one is to develop the detector itself. And this is called resistive plate chamber. This is actually 1 meter by 1 meter. Two glass plates will be separated by 2 millimeter, and whenever a charge particle go through that, it will give us a pulse. So we developed that in TIFR and built them slowly and developed them. All the electronics and everything is just homemade. There is nothing. You cannot go to a company and ask them that give me RPCs. They don't make it. So you have to build yourself. And then after we have developed ourselves and convinced that, okay, it is possible, then we transfer the technology to the company. And was actually this is, you can see the size of the detector. Okay, this is 2 meter by 2 meter detector, particle detector, each one of them. And these were brought from the factory, because then we transferred the technology to the factory, and now they have been tested and in our TIFR. And then these detectors have to be read by electronics. So these all electronics, if you see, they're all developed. All the electronics, are each of them, from the design to fabrication to testing to make it into boards, all done by our engineers and people develop those things. So this is a very exciting time for any student or anybody who have participated in those times. They have built and seen through this how to build a particle detectors and go from there. And then you put them all together. We have made actually many short, what we call prototype detectors, small scale, okay, not big scale, to see that everything is working fine. All the detector, all the electronics, they're tracking muons and so on. So this is actually, as you say, this detector will have iron plates. Okay, these will be magnetized. And between this gap you are seeing, in those gap, we will put particle detectors. So then in the result, whenever there is a muon is going through, it will go each pulses and it will give the position information from each of those pulses. So it will be detected. And then this is actually final form of that prototype that we have built in Madurai. This is the coil you can see going through all the iron plates. That coil is to magnetize those iron plates, because when high current will go, they will be magnetized through something like 1.5 Tesla magnetic field, and in between there will be those particle detectors that will detect the particles, and then they'll give us track like this. So these are straight tracks you can see, and because there is no magnetic field, but here you can see there is magnetic field, the tracks are bending. So from that curvature, we will know what is the momentum of that track and what is the energy of that event and what kind of tracks are there and so on. So this all have been established and we are ready to go to build the whole detector, and of course then the problem came and we cannot go any further. So this is the track momentum. So now I'll be just touching upon another final experiment. This is the ice cube laboratory, how big a neutrino experiment can be. See, this is at South Pole, and this is again international collaboration and spearheaded by Francis Halzen from the Wisconsin University in Madison, United States. And there, under the ice, use ice as Cherenkov detector. Like that, water has been used for Cherenkov detector. Here, ice is used for Cherenkov detector. And there, under the ice, you can see those. Here are the surface and the string, and these are all photomultipliers, covering an entire space of, entire space of 1 kilometer square and 1 kilometer in height, and at a depth of 1.5 kilometer in the ice at South Pole. And they will be detecting neutrinos of very, very high energy. I have talked about those astrophysical neutrinos coming. They can be of energy 10 to the power 12 to 10 to the power 16. MeV and so on, and those can be detected. These are the pulses, and from there, the pattern of those hits, you can find out the direction and energy of the neutrinos. Okay, so this is little complicated, but I'm just to give an idea what is the thing. You can have and put those photomultiplier tube in a bottom of the sea, and you see water when the particle goes, they will produce Cherenkov light, and all those photomultiplier will be watching and then detecting and making this detector again a kilometer cube detector. So these are for very high energy neutrinos, and this detector, this is came through net. This is coming in the Mediterranean by the European collaboration mostly. So now I will be having only two transparencies at the end. Then why India should be interested in such a project? And we just some playing toy for some from scientists or just so of course the excitement of carrying out this phone tracking experiment in a very important idea, in an area like neurophysics itself is very exciting, and you will be contributing to the world knowledge and science. Of course, it will address one key question of neutrino physics, that is neutrino mass hierarchy, but help us to pick up the correct theory beyond standard model of particle physics. We'll learn how matter behaves at extremely high energies existed in the early stage of the universe. I have already shown you one transparency. But this is not the reason. This is the science reason. But we'll develop various cutting-edge technologies for developing state-of-the-art detectors. For example, that big magnet, 50 kiloton magnet, 30,000 ton, those 2 meter by 2 meter RPC particle detector, sophisticated state-of-the-art electronics I was showing there. Online monitoring, data acquisition system, you write the software. Science students across the country will have the opportunity to participate in building each of these components from scratch. We are not buying from anywhere. We are just building whole thing and then putting it together and let them work as a particle detector. Many are already doing that. It will create an ambience of doing things with our own hand, a culture that is missing in India. And finally, of course, no single institute in India has the ability and resources for doing such it alone. So that is why already 25 research institutes, universities, IITs have joined hands to build INO laboratories and ICAL detector. Some are developing detector, some are developing electronics, some working on various engineering aspects, some optimizing the detector using computer simulation program. Culture of cooperation and collaboration is another benefit that will emerge from such mega science project like INO. Thank you all.
থ্যাংক ইউ নবদা। কারোর কিছু কোয়েশ্চেন করার থাকলে বলতে পারো। স্যারের সঙ্গে কোনো কোয়েশ্চেন যদি কিছু মানে আজকের লেকচারে যদি কিছু বুঝতে কারোর অসুবিধে হয়ে থাকে বলতে পারো। ওকে, তোমরা ভাবো। তার আগে আমি দুটো কথা একটু বলে দিই। আমি নবদা আসার পরে একটু কথা বলছিলাম। খুব দুঃখের ব্যাপারটা হচ্ছে যে অন্য কিছু জিজ্ঞেস করবি। খুব দুঃখের ব্যাপারটা হচ্ছে যে আমাদের দেশটা এতটাই দুর্ভাগা। নবদার সঙ্গে কথা হচ্ছিল এই আইএনও প্রজেক্টটা নিয়ে, যেটা নবদা বলতে পারিস একদম শুরু থেকে মানে এই প্রজেক্টের সঙ্গে আছেন। কিছু কি বলবো মানে অশিক্ষিত অর্ধশিক্ষিত মানুষের জন্য এই প্রজেক্টটা প্রায় মানে কি বলবো মানে শুরুই করতে দিচ্ছে না। কি না, তেজস্ক্রিয়তার জন্য লোকজনের ক্ষতি হয়ে যাবে। একটা এক্সাম্পল বলি, আমি ওই ডক্টর সিনহার লেকচারটা শোনার সময় শুনেছিলাম যে আমাদের বিভিন্ন মেডিকেল ইয়েতে ম্যাগনেটিক রেজোনেন্স ইমেজিং হয়, এমআরআই হয়। ওটা তো বেসিক্যালি নিউক্লিয়ার ম্যাগনেটিক রেজোনেন্স ইমেজিং। মানে নিউক্লিয়ার কথাটা ঢুকলেই লোকজনের একটা মানে অজানা আতঙ্কে মনে হয় যে এই মনে হয় রেডিও অ্যাক্টিভিটি হয়ে তেজস্ক্রিয়তা হয়ে একদম ক্যান্সারে মরে যাবো। এই আইএনও প্রজেক্টটাও ঠিক সেই কারণে মানে কি বলবো নানা বাধা বিপত্তির মুখে দাঁড়িয়ে আছে যে ওইখানে যদি কোনো আইএনও, নিশ্চয়ই বুঝতে পারছিস নবদা বললেন, আইএনও এক্সপেরিমেন্টটাতে আমাদের মধ্যে দিয়ে তো কোটি কোটি লক্ষ কোটি আইএন মানে নিউট্রিনো পাস করে যাচ্ছে, কোনো ক্ষতি হচ্ছে না। ওই তামিলনাড়ুতে গিয়ে ওইখানে ওই আইএনও এক্সপেরিমেন্টটা সেট আপ করলেই নাকি গোটা তামিলনাড়ু শুধু লোক রেডিও অ্যাক্টিভিটি হয়ে ক্যান্সার হয়ে মরে যাবে। এই সমস্ত বোকা বোকা মানে কি বলবো এজেন্ডা করে সাইন্টিফিক প্রজেক্টটা বন্ধ করে দেওয়া হচ্ছে। যেটা আমি আশা করব আমার ছাত্রদের কাছ থেকে, আমি এই লেকচারগুলো এই যে কারণে আমি অ্যারেঞ্জ করছি, সাইন্টিফিক টেম্পারামেন্টটা বানাও। ইট ইজ এ হাই টাইম। মানে অসত্য এবং কি বলবো অশিক্ষিত যে টপিকগুলো লোকজন বলে বা সেগুলোকে দাঁড়িয়ে একদম বলে আমি ফিজিক্স জানি, আমি জানি এটা দিয়ে কোনো ক্ষতি হবে না। প্রতিবাদ করো, প্রতিবাদ করা শেখো, কারণ তোমরা ফিজিক্স পড়ছো। ঠিক আছে? পার্টিকেল ফিজিক্সের রিসার্চে যেহেতু আমি নিজে এক সময় ছিলাম, কাজ করার মানে কি বলবো মজা, প্রচুর পরিমাণে মজা রয়েছে। একদম পিওর ফিজিক্স যখন আমরা পড়ছি সেটা তো একটা ইম্পর্টেন্ট বিষয়, কিন্তু এক্সপেরিমেন্টাল পার্টিকেল ফিজিক্সের যে মজাটা সেটা হচ্ছে যে তোকে একটা পুরো ট্রেনিং প্রসিডিওরের মধ্যে দিয়ে যেতে হয়, যেটা নবদা এই লাস্টের আগের ইয়েটা ট্রান্সপারেন্সিটা দেখালেন। আমাকে ইলেকট্রনিক্সটা নিজেকে বানাতে হচ্ছে, আমাকে ডিটেক্টরটা নিজেকে বানাতে হচ্ছে, কম্পিউটার সিমুলেশনটা নিজেকে তৈরি করতে হচ্ছে, কেউ আমাকে করে দেবে না। শুরুটা আমাকে করতে হবে। এবার দেখ ওই জিনিসগুলো দিয়ে আলটিমেটলি কখন কোথায় কি কাজে লাগবে না লাগবে আমাদের পক্ষে জানা না, কিন্তু প্রসেসটার মধ্যে একদম শুরু থেকে থাকাটা একটা জিনিস একদম শুরু থেকে আস্তে 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 গড়ে তোলাটা, এটাও কিন্তু নিজেকে মানে তৈরি করার জন্য বা নিজেকে সাবজেক্টের জন্য রেডি করার একটা ট্রেনিং প্রসেসের মধ্যে দিয়ে যাওয়া, এইটার কোনো মানে তুলনা হয় না। আমি একটা এক্সাম্পল বলছি, ইন্টারনেট তো আমরা সবসময় এখন ব্যবহার করি। ইন্টারনেটের জন্মটা কিন্তু সার্নে হয়েছিল। আমরা যে জিপিএস ইউজ করি, অ্যাস্ট্রোফিজিসিস্টরা সেলেশিয়াল অবজেক্টস গুলোকে ঠিকমতো প্লেস করতে গিয়ে জিপিএসটা ডেভেলপ করেছিলেন। যে টেকনোলজি ফিজিক্সের জন্য ডেভেলপ হয় সেটা আলটিমেটলি কিন্তু মানুষের কাজেই লাগে। ওই নির্বোধ বোকাগুলোকে কে বোঝাবে? তাদের বোঝানোর জায়গা নেই আমাদের কাছে। সুতরাং সায়েন্টিফিক টেম্পারামেন্টটা বানানোটা কিন্তু সবচেয়ে ইম্পর্টেন্ট, সবচেয়ে ইম্পর্টেন্ট। যারা ফিজিক্স পড়তে ঢুকেছো, সায়েন্টিফিক টেম্পারামেন্ট বানাও। কোনো মানে নিজে যাচাই করে, নিজের হাতে করে বা নিজে বুঝে নিজে পড়ে সেটা থেকে যে অ্যাকচুয়াল ট্রুথ বা সত্যটা বেরিয়ে আসবে সেটাকেই বিশ্বাস করো, আর কারুর কোনো কথায় বিশ্বাস করবে না, কারণ তুমি ফিজিক্সটা পড়েছো এবং তুমি জানো। আর যদি কারুর কিছু কোয়েশ্চেন থাকে, তাহলে নবদাকে থ্যাঙ্কস দিয়ে আজকের প্রোগ্রামটা আমি শেষ করছি। লিপিকা দি, এইটা একটা সামান্য উপহার নবদা। এরা তো আমাকে আগে থেকে বলে রেখেছে আপনার সঙ্গে ছবি তুলবে, সেই ছবিটা আপনার কফিটা সবাই খেয়ে নি, তারপরে আমরা ছবি তুলবো। হ্যাঁ, স্টপ করে দেন। আচ্ছা, কিরণ লাইভে কোনো কোয়েশ্চেন আছে? পরে মনে হয় করবে। লাইভে কোনো কোয়েশ্চেন করেছে? ঠিক আছে, ওকে, লাইভ বন্ধ করো।